In this video, I'm going to talk about something called the common ion effect. And this goes along with section 17.1 in your textbook. It starts on page 720. And then I will also do another video where I'm going to show you how to do the math with a common ion. So for right now, I want you to think about a solution of, let's say, 1 molar hydrofluoric acid. And so we know in this solution we have some hydrofluoric acid molecules, and then we also have some hydrogen ions, and we also have some fluoride ions. Water's in there as well. I just didn't write it in this equilibrium. I could have written it with water present, and then I would have hydronium ion instead of the hydrogen ion, but I chose not to write it that way. So we're not going to worry about that. But that's really what's going on in there. So I'm going to draw a bigger picture of this. So I've got water. I have some hydrofluoric acid molecules. Let's just do 5, even though there's way more than that. And then I have a very small amount of hydrogen ions and fluoride ions. So I'm just going to do one of each because that's a smaller amount. Now let's say to this we are going to add a 1 molar sodium fluoride solution. So there's water present here, and we know that sodium fluoride is a soluble salt, so it's going to completely dissociate. So that what that means is we get 100% ions. So in this solution, there's no molecular sodium fluoride that you're going to see. So in here, we would have let's see, 1, 2, 3, 4, 5. Okay, so if we combine those two together, we're going to have something like this. And what I want you to notice is that in each of these dissociation reactions, we have a fluoride ion. So if we look at this solution, we have fluoride ions that come from sodium fluoride. And then we also have, I think I found them all, fluoride ions that come from hydrofluoric acid. So that ion, the fluoride ion, is called a common ion because it is common to both of those dissociation reactions. Now there's another definition for it, which we'll talk about in a minute. So what I want to do is look at this a little bit more. This is a weak electrolyte. So if we had taken our little conductivity meter and we had stuck it in this solution, so let's say we have a light bulb, that light bulb would only glow kind of dimly. If we had taken our conductivity meter and had stuck it in this solution, it would shine really brightly because sodium fluoride is a strong electrolyte and we get 100% ions. So what we want to do is we want to look at this dissociation reaction for the weak electrolyte. If we only had this, which is what I had drawn in the first example. So let me get rid of this arrow because you already know I added it to it. Let me sketch this HF solution one more time. So I've got lots and lots of hydrogen fluoride. and I have just a little bit of hydrogen ions and fluoride ions. Okay, so I'm looking at this equilibrium. If you think back to Le Chatelier's principle, if we take something that is common to this equilibrium, so in this case the fluoride ion, and we are adding more of this fluoride ion, what we are doing is we are increasing the concentration of that ion. And in this case, we're calling it the common ion. So if we increase the concentration of our common ion, what happens is the equilibrium is going to shift toward reactants to reduce the stress. So what that means is our equilibrium constant would get smaller. There would be fewer H+ ions present. And so what would happen is, if you think about the equilibrium reactions that we've done, where we've done math with them, this shifting back toward molecular HF makes this solution much less acidic than it would be without the addition of the common ion. So let's look at this as an official definition. So the common ion effect, as defined in your textbook, states that whenever a weak electrolyte, so this is going to be like a weak acid or base, and a strong electrolyte, this is going to be your salt, contain a common ion. And so what you're going to do here is you're going to look for what's similar or what's the same. And it's going to be an ion in the salt. The weak electrolyte, so that means your weak acid or base, ionizes less, so that means shifts to the left, which means Ka is going to decrease, and that will also mean that hydrogen ion concentration or hydroxide ion concentration is going to decrease as well than it would if it were alone in solution, and that would be just the weak acid or base itself. So let me do another example. Let's say we've got ammonia, and we're going to have ammonia in water. So you know ammonia is a weak base. It's going to accept a proton. We will get ammonium and hydroxide ion. So lots of this, just a little bit of this. And then let's say to this equilibrium, we are going to add, let's do light blue, ammonium chloride. So we're going to add some ammonium chloride to this, soluble salt, so it's going to completely dissociate. So I've got 100% ions here. And if I take a look at these two, all this stuff is combined together in my beaker. And really, because this is a soluble salt, as long as it's not saturated, it's not going to be there. But I'm going to go ahead and put it back. If I look, the ion that is common to or present in both of those reactions is the ammonium ion. So that is our common ion. So if I go back and I look at this, whenever a weak electrolyte, here's my weak electrolyte, and a strong electrolyte, here's my strong electrolyte, which is my salt, contain a common ion. My common ion is the ammonium. The weak electrolyte, that means my ammonia, ionizes less, so that means I have less of these two ions than it would if this were not there. if the ammonium chloride were not there. So what that means is that I have less hydroxide ions present in solution. And that's in line with Le Chatelier's principle, because if I increase the concentration of this common ion, it will shift the equilibrium back toward the reactant side, which would mean concentration of both of these would decrease. Okay, this video is done. You can watch the next video if you want to learn how to do math for common ion.